Namaskar students. So from this lecture we are going to start our new topic, that is stability of your control system. So up till now we have discussed how we can obtain a time solution of any kind of system equations. Okay, so previously we are discussing about whenever we are having a first order control system or the second order control system, when it is subjected to unit step signal, unit ramp signal, impulse signal, parabolic signal, how our system is going to behave. Okay, now this output is nothing but a independent variable as a time. Okay, so if we are varying the value of time, your output is going to be vary. Okay, so for some part of the time your system will be stable, for some part of the time the system will be unstable, or we can say the vice versa, or for we can say the entire period of time it might be stable or it might be unstable. So how we can define the stability of the system? So whatever the solution that we got in a previous chapter, it can be classified into two categories. The first category is the one wherein the output tending to a finite value. Okay, so this is nothing but, let's say this example, you can see your output is changing. Here you can see the value is somewhere around here, but after some point it is going to settle down. Okay, so we're going to get the steady state value after, let's say, t is equal to 20 seconds. Okay, so this is one kind of system. The second is the other where the output approaching towards the infinite value with the advancement of time. So as we are increasing the time, you can see the response of the signal is increasing. So it is going to increase as time is increasing. So there are the two kind of solution will be there. Okay, so roughly speaking, what is the stability? The stability is nothing but a system that implies that a small changes in system input in initial condition or in a system parameter do not result in a large change in a system output. So what do you mean by stability? Is nothing but whenever we are changing your we can say here it is system parameters or with initial condition. So is there any small changes in system parameter or initial condition? Yes, in that case we have to check whether our output is changing or not. If it is minor changes, then we can say our system is stable, but if it is a large change in system, it means our system is unstable. Okay, so I hope you get it. This is the, we can say, a simple definition of the stability. Now here we have two example. Let's say it is the stable system. From the behavior we can identify that after some time this oscillation will damp out. Here the oscillation is increasing as time is increasing, so it is unstable system. So whenever a bounded input is applied to any kind of system, let's say this transfer function of the system is given by g1s divided by 1 plus g1 into h1. Okay, so whenever this system is given by a bounded input, okay, so for when we are finding the time response of the system, let's say we are getting such kind of oscillatory response. Okay, so the time response is also bounded, because we know that at time increasing this oscillation are going to be damped out, and this kind of system is known as a stable system. Okay, on the other hand, the system shown in this figure, we can see that the output of the system is unbounded. Okay, the value is going to be increasing as we are moving towards the infinity. So this kind of system is known as a unstable system. Okay, so whenever we are applying a bounded input, in that case your output should be bounded. So we can say the system is stable system, otherwise it is unstable. Okay, so the first thing that you have to keep in mind, that for a system that is excited by bounded input, and for that your output should be bounded. Okay, so here that's why it is stable system and it is unstable system. The second thing is in the absence of your input, so whenever we are not applying any input, okay, when it is r of s is equal to 0, in that case our output tends to be 0 also. Okay, because we are not applying any kind of output. In that case your output should be 0, but due to some initial condition we will get some value of output c1t and c2t. Okay, so in the absence of input, the output tends towards the zero. It means we are talking about the equilibrium state of the system. Okay, irrespective of the initial conditions. So this kind of stability concept is known as asymptotic stability. Okay, now this whether the system is stable or unstable depends on the behavior of the system, and behavior depends on the location of poles and zeros of the system. So once we know that this much of pole is lying on j omega axis or the real axis, we can in short we can say on a z plan, we can identify the behavior of the system, and once we have the behavior of the system, we can say our system is stable system or unstable system. Okay, so now let us understand how your poles and zeros will be there. So let me just, I hope it is visible to everybody. Okay, fine. So here you can see there is a root in S plane. It means whenever we have such kind of system, we find the roots, or we can say the values of poles. So here it is an corresponding impulse response that we have plot. Now we know that whenever we have dealt with your first order system subjected to unit impulse signal, in that case your C of t is nothing but capital T e raised to minus t by t. Okay, so your behavior of the signal will be exponential. So that is okay, this is nothing but, let's say this value is a. Okay, so this transfer function will become 1 divided by s plus a. Is nothing but your, let's say this transfer function directly t of s. Okay, so this is first order control system, and we finding the impulse response, you will get such kind of response. Same way, when the value of value of root is positive, let's say it is plus, here it is minus a, in that case you will get such kind of response. Okay, so here for bounded input we are getting the bounded output, so we can say this system is a stable system, and this will be unstable system, because with increasing in time your system behavior is going to increase only, so this system is unstable. Same way, here we are two poles, that is in a left hand side of your j omega axis. In that case we will get some kind of oscillatory response. Okay, I am not finding this all this response, but you can easily find your impulse response for this particular function. Okay, so if you find this, you will get such kind of response. So here you can see that as time is increasing, your oscillations are damping out, so this system is also stable system, and here you can see it is unstable system. Same way, when two poles are on j omega axis, or we can say imaginary axis, at that time this is the response of the function. So here we can see the response is not changing, it is not damped out, or oscillations are not increasing. So this is nothing but it is not the stable system or not the unstable system, but it is marginally stable system. Same, when double pair of the roots are at the same location, if you find the response, it is going to increase and increase. So this is nothing but your unstable. Okay. Same, whenever you find a root which is located at your origin, this kind of your response will be there. It is nothing but your marginally stable, and when double roots will be there at origin, it is unstable. Okay, now the thing is that how we can just find whether the system is stable, unstable, or the marginally stable. So if all the roots of your characteristics equation have the negative real part, okay, negative real part, it means it is lying on the left hand side of your j omega axis. Here you can see it is having a negative real part. Same, in this case, let's say this values, if we find this is, let's say it is a real part is minus a, and your imaginary part is, let's say it is 2. So we can say it is minus a plus 2j Same, this will be minus a minus 2j. Okay, this will be minus 2. Okay, so of all the roots of the characteristics equation have the negative real parts. So here the real part is negative. Same here also, the real part is negative. The system is stable. Okay, so here you can see the system is stable. Same way here the system is stable. Okay, so only thing we have to keep in mind that all the roots of your characteristics equation should have the negative real part to be stable. Okay, now the second thing is, if any of the roots of your characteristics equation has the positive real part, or we can say if there is a repeated roots on j omega axis, the system is unstable. Let us first talk about this term only, the positive real part. So here you can see a real part is positive, that is plus a. In that case your system is unstable. The second is, here you can see it is nothing but, let's say it is a, then a same, let's say it is 2 minus 2, so a plus 2j, a minus 2j. So don't worry about what is your imaginary part, but if your real part is positive, in that case your system will be unstable. This is, you can see there. Okay, now the second thing is, or if there is a repeated roots on j omega axis. Okay, so here we are getting the roots on j omega axis. Okay, but this is the different case. Here we are talking about repeated roots on j omega axis. So here you can see there is repeated x, because this value is, let's say 2j, it is also 2j, it is minus 2j, the second root also minus 2j. Okay, so two roots are lying on the same location. Here also two roots are lying on the same location, so we are getting double pair of the roots. In that case also the system will be unstable. Okay, same, you can see this, two roots are lying on your origin, so your system will be unstable. So okay, these two things are very clear. If all roots are on the left hand side of your j omega axis, then system will be stable. If any root is right hand side of j omega axis, your system will be unstable. Okay, when two pair of poles are on j omega axis, then system will be unstable. And the last condition is one or more pair of pole that is non-repeated on j omega axis, then we can say it is marginally stable system. So we are talking about this scenario and this one. Okay, here you can see your poles are on imaginary axis and they are not repeated one. If it is repeated one, in that case it is unstable, but these are the non-repeating poles, that is why the system is marginally stable. Same here, we are getting one pole that is at j omega axis. It is also on real axis, but it is also on j omega axis. So such kind of system is a marginally stable system. Okay, so in short we can write that. Let me just show you. So the region of your stability, let's say this is your imaginary axis, your real axis. So in z plane, whenever our roots is on the left hand side, then it is a stable system. Whenever our roots are on right hand side, then it is unstable system. And when our roots are on this imaginary axis, then it is marginally stable system. Okay, so this region of stability is very important to identify whether the system is stable or not. However, the simple, or we can say the graphical or the algebraic method have been developed, which is give us a study of stability of the system without need of actually determining the roots of your characteristics equation. Okay, so we don't have to find out the roots of your characteristic equation, but we know the position of the roots of your characteristic equation. Okay, with using Routh Hurwitz stability criterion. Okay, so this is very important because it will give us the position of roots on your z plane. So Routh-Hurwitz will not give us the value of your pole, okay, but it will give you the position of your pole on Z plane, and on the basis of your position we can identify either your system is stable, unstable, or the marginally stable. So whenever we meet in next lecture, we are going to discuss about Routh-Hurwitz stability criterion. Okay, thank you.